Um, Good afternoon, everybody. I will welcome you all to our webinar, which will be about the safe and autonomous transport of goods in the factory shop floors using 5G, which is part of the central node, and we as a CCI will present it. For your information, all of this webinar will be recorded, and if you're okay with it, you can stay in the room and watch our webinar. Yes. So I will start with introduction. First of all, I want to present ourselves as a company. Who are we, the CCI? Our main goal in CCI is basically to accompany a potential customer or a customer from a normal production, and the customer wants to improve, for example, the production, how quick we can produce goods, to an intelligent production with optimizing systems, forecasting capabilities through information and transparency through data. And we as CCI accompany the whole process from like transparency through data, forecasting, transparency through data, as you see the following steps, to like a full smart and intelligent production. So the customer comes to our company and with a specific problem, we present them potential solutions, and yeah, as I said before, we advise them, giving them advice how we can solve certain problems. The main key here is that we already have knowledge due to our big community about certain technologies, a lot of them like the digital twin or AR, VR. And from the other side, as you can see in this slide, the customer comes with the challenges they are facing. And then we meet in the middle and find a common solution how we can improve the whole process. As I said, we are not a classic consultant. We are a community. We benefit from the scientific research from the university side, and also from our company partners that also have a lot of informations and experiences. And together with the community knowledge, we try to improve the customers' production, for example. So let's also dive into the CCI's roles in Zero Storm. The CCI are members of the central node, which also several other partners like ZIG, which we also collaborate in the trial a lot with, are also in. And therefore also this trial that we are going to explain right now is within the central node and is about, as I said initially, 5G-enabled AMR transport. Our role was like tech integration, testing and optimization, and improve automation, safety and coordination in intralogistics. How we do that? One of the key points is that we can provide a very realistic real-life testbed, the demonstration factory in Aachen, which we used as a testbed facility for a lot of trials. Also our trial, because we have a 5G private network we can use for specifically also our trial. And we have crossings, we have a very real-life production hall. So we can test a lot real-life situations and scenarios that we will also explain, especially at the end of the presentation. So what is the Trial 1 about? What is the initial idea of it? So AMR currently are facing lack of visibility beyond direct sites, limiting safety and efficiency, which means, okay, when the AMR is driving towards a crossing, it cannot look around the corner. So with the help of various sensors and also a computer that is connected with both of them, we can solve this problem. And also a key point here is the 5G enabled improvement. So we can do that very seamlessly and also in real time with 5G. And now I will explain the two main assets, I would say, of the use case. First of all, we have the AMR, which is the ClearPath A200 Husky. This AMR uses SIG Multiscan 100 and two SIG Microscan 3 Pro sensors for safety and localization, which are ideally mounted on the Husky. Edge computing is handled by the onboard Think Center PC, which is also mounted in the AMR. And the Think PC runs microscan sensor nodes for real-time data processing and also the multi-scans if it is mounted. And as I mentioned before, the testbed is the demonstration factory Aachen, the DFA, how we call it. And you can see on the left as before, and also on the right, the corresponding map that we had to create to make navigation possible. As I said before, the key point on the DFA is that we have a 5G network that is crucial for the whole trial. And now, to create a better understanding, in the following slides, we will first explain the hardware of the trial, which, for example, can be the AGV, and also the system software, like the other side. And my colleague Anjali Gupta will start with the hardware side and explain in a detailed way what hardware we use and what it's for.
Hi, Shkalshan, thanks for the introduction. And yeah, so mainly I'll initially talk about the AGV and the hardware that was mounted on it. So we have the 2.6 sensors, as Shkalshan talked about, and the TDC, which is the telemetry data collector, and the onboard PC. Now, going into more detail, we have the properties of the Husky itself. It has it is an all-terrain vehicle, so it's very suitable for scenarios like in a factory environment. It is mounted with an aluminum plate, and we also manufactured steel the steel plates for mounting the sensors on it. It has a lead acid battery, which provides a operating time of 3 to 8 hours, and it has multiple power supplies for different peripherals like 5 volt, 12 volt, and 24 volt supply, on which the operating time differs. And the maximum speed is 1 meter per second, which is quite quick for factory environments. Yeah. Moving on, we have the back panel of the Husky, which provides information on the right side. We have the power button, the battery level indicator, the communication, and other information like stop and error. And the battery, as we can see, that it tells the battery level. And under it, it's the communication light, which tells how well it is connected to how well is it wirelessly connected. On the left side, we have the emergency stop button, which is used for emergencies, and it can be disengaged by rotating it back into place. Moving on, we have the sensors used. So the 2.6 sensors that we used, the first one was the ZIG Microscan 3 Pro, which is an advanced 2D LIDAR. It has a range of 275 degrees and a safety range of up to 9 meters, which means basically we can have extra safety information within a 9-meter range with its ROS2 package. And it was the primary collision avoidance sensor for the AMR itself. And it was used for the localization, the local cost map, and was also used to create the map for the DFA, as you saw in the previous slide. Then the second sensor was the Multiscan 100, which is a 3D LiDAR, which is used to generate 3D point clouds. It's used for object detection and mapping as well. Here we used it as an infrastructure sensor and on the AMR. So on the infrastructure sensor, we used it for creating a safety zone on the crossing, which gives the idea of how we can see around the corner for the Husky to know that something might be around the corner, which clearly it cannot see with its line of sight vision. And then it was also used on the AMR itself as a direction vector generation for obstacles to predict how moving obstacles will move if they are moving, and it can then it will be further emphasized on in the software part. Then moving on to the industrial computers used, the DIMA was a data integration and mobility analyzer, which receives data from the TDC and the infrastructure sensor, puts them all together, and sort of runs the navigation and nodes which bring the whole system it acts as a central node for the whole system. We're moving on to the telemetry data collector, the TDC, which was mounted on the AMR itself. It helps gather, process, and transmit data from the AMR to the DIMA. It has 5G capabilities. It gets all this information from the AMR sensors like the microscan, multiscan, and the IMU sensor. It puts it all together, processes it for the localization. So the collision avoidance is running locally on the Husky itself, and then it also sends this data to the DIMA for running the navigation, which we'll see how it happens later on. Moving on to the more important and like the main part of this presentation, the 5G. So if a device is not 5G enabled, like the DIMA was not, um, we use something like the Cradle Point, which is a 5G router, which has two SIM slots, in which you can put 5G SIM cards, and it has 5G antennas, and it can be connected to any device over Ethernet, and it provides it 5G network. It also has Wi-Fi router-like capabilities, so your 5G network can be converted into a Wi-Fi signal for multiple devices connected to the same 5G SIM card. And it is provider dependent, so we have a couple of providers for this 5G network in the DFA. And moving on to the private cellular network architecture that we have in the DFA, there are two kinds. There is the slicing and the independent private network. We have the latter one, and the DFA is equipped with two of these providers. We connect devices to this 5G network using 5G hats, which can be mounted on Raspberry Pis or industrial 5G routers like the Cradle Point, as we saw earlier. So in this, it is a better. It generally depends what kind of a network you want, but like we used an independent private network just to have a firewall between the public 5G network and the agents that we have inside to maintain security. And this security is maintained by firewalls, which is maintained by the provider itself. And it's better in the way that we have more bandwidth as there are no external agents working on the same bands of this 5G network. We have our own towers and our own antennas indoors in the DFA. Then moving on to the overall network architecture and the hardware architecture summed up, we start on the left, on the right with the AGV, with the AMR, and the TDC collects all the data from the AMR onboard PC, the multi-scan 3, microscan. All this data is collected by the TDC, of course, with a network switch. And all this data, since the TDC has 5G capabilities, it sends it to the Cradle Point, which receives it and transfers it via an Ethernet cable to the DIMA. And also the infrastructure sensor gives the data over Ethernet to the DIMA. And this sort of creates a whole architecture where the the AMR is sending its location information to the DIMA, so the navigation can know where the AMR is, and the infrastructure sensor creates this safety zone in the map itself, and we have a whole safety system in place. Now, moving on to the software part, my colleague Ivan will take it from here.
Yeah, thank you, Anjani. So now let's talk about the system software. And firstly, I would like to give you an overview of the main software packages that we use in this project. And on this slide, you can see our main ROS2 related packages like Nav2, Gazebo, Slam Toolbox, Arbis2, and let's talk about each of them specifically now. So firstly, ROS2 stands for Robotic Operating System 2, and it's an open source robotics framework designed for building robot applications. And though it's called operating system, it's not quite an operating system. It's, as I said, more like a framework. Though we can find similarities between a normal operating system we used to have with ROS2, for example, as an operating system manages different applications on a laptop or a smartphone. ROS2 manages different nodes that handle specific tasks. So each node should be responsible for a single modular purpose. And for example, like controlling the wheel motor or like getting or receiving the sensor data from a laser scanner. So each node is responsible for some sensing, moving, processing, and so on and so on. And all the nodes within ROS2 framework can communicate with each other when they get the data, when they send and receive the data from each other. And the key feature of ROS2 is that even if some different nodes are running on different devices, but the devices are within one same network, they can explore the nodes across all of these devices, and they can communicate with each other when they are in the same, for example, 5G network or Wi-Fi or local network, doesn't matter. So in our case, it's 5G. And now let's go through some other packages like SLAM Toolbox. So firstly, we will need to create a map of our DFA, of our fabric. And to do that, you can see the animation of the visualization of the mapping in RViz2. That's the package here. And also we launch SLAM Toolbox to create the map. So to do this, we drive the Husky manually with a joystick because it doesn't know the surroundings yet. So we have to drive it manually so that the SLAM Toolbox can get the data from the microscan sensors, and it can explore the DFA surroundings like you see in the animation that it explores the whole map that you see, for example, on this slide here. So that is the final result of the mapping. And further, we can use nav2 navigation stack package. And its three main functions are localization, path planning, and collision avoidance. So localization means that the robot should find itself on the map, so where it actually is right now. And it should be also dynamically updated when the AMR changes its location, for example, when it goes from point A to point B. And to be able to move it from point A to point B, the nav2 stack is used for path planning. So it calculates optimal routes for autonomous movement. Also, it detects and avoids obstacles dynamically, which means so when the AMR is running, when it's driving across DFA, it should avoid some static or moving obstacles. And for that, also the sensors, the safety sensors are mounted on it to prevent collision. Later on, before we actually deploy all the software and navigation packages on the robot itself, we should test them. So to prevent some risks of collisions, of damage, and so on. So for that, we use Gazebo that you can see also in the picture. So Gazebo is basically a simulation of the packages, of the software packages that we can use. And we can test out everything. So again, the collision avoidance, the path planning, the driving of the robot, because it's the full simulation just on a software part. So we do not have to try it out on the real robot. So we do not crash accidentally into something or someone because we have some bug in the software. So as soon as we know that everything is safe to go, after we tested everything in Gazebo, we can proceed with further implementation. And when we mapped our DFA, when we deployed the navigation stack on the AMR, we can divide the map into different parts of it. So that means the resource definition, the resources are intersections and lanes. Those are the parts of our map. And they have also different subtypes that you can see. Some of them you can see on this slide, like omnidirectional intersection or bidirectional lane. And first main reason for that is when we restrict some areas to some specific directions that an AMR can go through, we can basically simplify very well. We can simplify the collision avoidance and the path planning. So mainly it's very similar how we have the roads mapped in real life, like we have a street and the cars, normally they cannot go in any direction they want. Usually it's regulated by some rules. So similar idea we have here. So that if two AMRs, they drive on different sides of the two lane, as you can see here, then it means they should not accidentally crash into each other. And the second reason why we need this resource definition, I will explain a little bit later when it would be clear from the context. So later, when we have here, we want an AMR to execute some order. And for that, we have a user interface, so a dashboard that you can see on the left of the slide as a screenshot of it. And it is deployed on the edge computing device that can be placed, for example, in the infrastructure. And a user can define an order. So an order in this case is a combination of 3 possible actions: go, pick, and place. And an example cycle you can see on the left. So it's just an example cycle. So for example, there could be more actions, there could be less actions, they can be in different order, doesn't matter. So a user defines in the dashboard to which location an AMR should go, at which location it should pick something, and so on and so on. And after that, it clicks the send button. So it clicks the send button to execute an order. So what does exactly happen when we click the send button? Let's see. So on the edge device, we also run the centralized controller, so a part of the dashboard, and it has 2 modules in it. So firstly, it's a task manager, and secondly, it's a resource manager. So task manager is divided into 2 sub-modules, a job dispatcher and a status tracker. So a job dispatcher is exactly the sub-module that assigns a task to an AMR. So after we click send, the job dispatcher finds the closest available AMR at the current moment and assigns an order to it. Then a status tracker changes its status from idle to running, and the AMR starts executing the job. So after that status tracker, so it's a tracker, it tracks its status until the AMR reaches the goal position, the target position defined in the order. And as soon as it is reached, then the status tracker updates the AMR status again to idle so that it can again be assigned a job and be used later. So that's about task manager. So a resource manager, it manages resources and their request queues. And by request queues, we can go back again to the resource definition. So as I said, we not only divide the areas of each lane or an intersection into specific directions. It can also appear when we have multiple AMRs in a DFA. It can also appear that some specific resource, for example, intersection, is already occupied by the critical number of AMRs. And that means if one more AMR wants to drive through this intersection, it cannot do this. We cannot allow this to prevent some collision. For that, we need to properly distribute the resources, and that's where we need request queues. So each task has its priority. So a user defines a priority of his order, and after that, if we want to decide which AMR gets the resource first, so if we want to decide which AMR should go through the intersection the first and which one the second, we would need the priority of their task. And that's exactly what the resource manager is responsible for. So it deals with requests. So for example, an AMR wants to plan a path, and it's added to the queue or to the request queue of each resource intersection it's interested in. And let's now see how exactly the prioritization is working here. And we see, we should better understand it on the example. So let's say we launch an AMR with priority 2, and it wants to go through some intersection that is occupied. So it waits at the intersection, and it should wait until his turn is coming. After every other AMR with higher priority is already gone. So it waits, but if we do not change its priority, it can appear that it can change arbitrarily long time, and we do not want this because otherwise it will be infinitely postponed until there's no AMR with higher priority. So we do not want this infinite postponement. We have to make a delayed AMR with higher priority. So we define an increment period, let's say 30 seconds, and that means every 30 seconds we increase its priority so that it doesn't take forever to take the intersection. So it waits 30 seconds, it switched to priority 3, then to priority 4 in 30 seconds again, and now it appears that this AMR is now the most prioritized, and the now intersection can be released to it as it's on the top of the queue. So this is basically how our resource prioritization and allocation works, so that we can have more of a big picture of all of our components. First, we have our edge device, where the dashboard is deployed and the task and resource management is happening. So resource allocation, task prioritization, job distribution, and so on and so on. After that, we have single AMRs. They plan the path regarding their order. They adjust the path depending on the obstacles they meet, and static or moving. And also they get help from the infrastructure sensors, because the infrastructure sensors, they cover blind spots at the intersection when an AMR cannot see, for example, if something is coming from the corner and so on. So the infrastructure exchanges the status if the intersection is free or is it occupied, so that AMR can also accordingly change the path, or it can safely come through. So if some intersection is occupied, it can either slow down or wait until the intersection is free again, or just to change the path to drive around. And the complete picture of the software architecture, we have an AMR with a TDC on it, and then it exchanges data with DEMA at the infrastructure. So, and that is connected to infrastructure sensor that gets the data from the blind spots. So each of these modules, let's take a detailed look at these functionalities. So on the TDC of the AMR, we run 2 nodes on the Husky, so the obstacle direction vector creator and the obstacle avoidance. So the first one is getting data from the multiscan, and it is used for getting the direction of some moving obstacle. So if something is moving, we get the direction vector in which it is actually moving. And the second one, it's getting data from the microscan sensors, and it's used for the safety. So it's for the obstacle avoidance. Also, infrastructure sensor, also multiscan, it gets the data from the intersection, and it creates and sends point cloud data to the DEMA, which is used to create the crossing zone. The DEMA gets the data from both, so from AMR and the infrastructure sensor, so it basically has the overview of the whole intersection, and it also can see what is moving in the intersection. It can say the status of it, and it can not only say if the infrastructure is free or occupied. Knowing the speed and direction of the moving objects, it can also predict how the status of the intersection will change over time. So now I would like to hand over to Kacim again to talk about 3 scenarios.
Thank you both for the good and very detailed explanations of the hardware and the software side. So now that we have all the tools understood to actually execute the trial, we want to showcase the results and the actual trial that we managed to bring to real life in collaboration with our fellow partner ZIG. And for that, to make it like a full use case, we have an intersection and 3 scenarios. The first one is no obstacle. So when the intersection is free and the AMR can move towards the crossing. The second one is with a static obstacle, which you can see also in the picture, how the AMR reacts and moves around it. And the third scenario will be the AMR, and around the corner there will be a dynamic obstacle, which can be a human person, or if we have a fleet, another AMR. And in the following, my colleagues will explain how now, with all the tools that we understood and that got explained, how they interact with each other so that the trial and the use case will work, and how it actually comes to real life.
All right, so let me begin with the first scenario. Here we see that in the intersection there is no obstacle. So the main goal of this scenario is that AMR safely drives through the intersection without changing its path. Now let's see, we have again 2 animations. So on each of them we see the ARVIS 2 visualization again and the map. Also on the map, we see the intersection zone marked in different colors. So I'll explain what it means exactly pretty soon. And we also see this little red line, which is the planned path of the actual order the AMR is following. So it goes from point A to point B through the intersection area. And on the left, you can see the case where we have the infrastructure sensor turned on, and on the right, we have no infrastructure sensor, so we have no blind spot detection, so additionally to the AMR. Okay, so let's begin with the first one with no infrastructure surveillance. And in this case, we cannot be sure that the AMR actually can drive through the intersection safely or not, so we always slow it down, so it always slows down as soon as it reaches the intersection area, and until it goes out of it, it always runs with a slower speed. So running the navigation stack, it localizes itself, and as the intersection is a defined area in the map, it can know itself that it enters the critical zone and it has to slow down. But when we have a surveillance available, we have the infrastructure and we have the sensor, and the sensor can let us know that the infrastructure is free, so it is safe to go and we do not have to slow down. So the sensor sends the data to DIMA, and over 5G, the AMR and DIMA, they exchange information that AMR doesn't have to slow down. So when the intersection is green, it can safely go through it without changing the speed, without changing the path. And here you can see the real life scenario with some small AMR perspective view in the small box. Okay, so now for the rest, for the 2 last scenarios, I would like to hand over to Anjani.
Yep. So in the next scenario 2, the environment looks a bit different because this is the DFA. The previous one was the ZIG facility in Hamburg. And in this, we have a static obstacle instead of no obstacle compared to the last time. On the right-hand side, you can see the ARVIS 2 visualization, where the clouds that you can see in lighter color are the global cost map created from the navigation, and the darker clouds that are around the AGV are the local cost map created on the spot by the AGVs, AMR's sensors. Now, in this scenario, we basically see that the AMR detects something which is static in its path. It recorrects its path and starts moving without colliding with the static obstacle itself. And this is done by setting, so the navigation knows where the initial position of the AMR is, and then we set the goal position, and then it just goes around, sees the obstacle, and then it navigates around it by itself, and then goes past it to the goal position. This is important because we do not want it to collide with any obstacle that might be lying around in the factory environment. And it's yeah, that's it for this scenario. Moving on to the more exciting scenario with dynamic obstacle, where we combine all of the two previous scenarios and add movement to the obstacle itself. Here we can see that we can see the infrastructure sensor at work when the obstacle in the blue box enters the crossing. The intersection turns from green to red, from yellow to red, and thus the AGV knows and slows down for the object to pass. And the multi-scan also creates a direction vector predicting where the obstacle might be heading. So, which is important for the AGV to, for the AMR to sort of move around the obstacle and not collide with it. This all of this is connected over 5G. So the infrastructure sensor lets the AMR know that you need to slow down, and then when the obstacle passes, it can move freely. Yeah, that in this scenario, our obstacle was a human. It could have been anything else as well. We just predict the size using the multi-scan sensor, which was at the infrastructure. And now moving on to the future perspectives, Shikalchan will take the stage.
Thank you for the good elaboration of the use case. So now that we know, okay, we have an AMR in the factory, and we elaborated and tested the potential scenarios that could happen in the intersection, and do also with the connection through 5G and the rest of the testbed that we described before. There are two key technologies that, in our opinion, could be very good future enhancement of the use case. The first one would be the asset administration shell, which you can see on the left side, which is basically, as the name says, administration shell, and our asset here can be or is, as we see in the picture, the AMR. And the administration shell contains submodels. The submodels are those names that you can see in the green box. For example, the identification, technical data, documentation, operational data, etc. It can be basically a lot of categories. And those submodels contain variables and constants. For example, the identification contains what does the, in our case, the AMR look like. The documentation can catch, okay, what is the history of the AMR, which path did it go, and the technical data can be, for instance, the velocity, and which is in that case a variable. And on top of that, which we would, those are two separate technologies, but in our opinion, the combination of both would be ideal, because the AAS supports actually a creation of a digital twin. So in the creation of digital twin, we create what the name says, a twin, and that through 5G, which is like the backbone of the whole trial, can be created. And yeah, let's start a little bit with the AAS, since I said it's the first step of a future enhancement. As I said before, the asset can be an AMR, but the AAS is can be an administration shell for like every other asset also. Like what an asset is more of a philosophical question. So it can be equipped everything. For example, the infrastructure sensor, which also contains then submodels. For example, the range that Anjane mentioned before. Also the user and yeah, every AMR basically. And as you can see in the architecture on the left, the yellow boxes that like equip the assets is the AIS in this architecture. And the AIS can then improve the whole administration, as the name says, that we can track every data and every variable and constants, and also the changes that are initially immediately in the shell, and so available for every user to use to read and to work with that. And the first benefit also leads to the second benefit. The AIS is unique. What does it mean? So every asset, for example, our AMR, the Husky, has a barcode, which is unique and only for that one Husky that we, for example, showcased. Not even that if we have two of them, there are two different barcodes. So this barcode has the information for another AS, for example, that collaborates, that it immediately knows, okay, with what kind of asset am I working right now? This will improve the adaptivity of every factory that uses different technologies, which is often a problem if you use different technologies to if you want to integrate a new asset. It can be a problem due to lack of flexibility, and that's what the AIS intends to solve. So besides that, then, as I always said, the real-time synchronization due to the information can be improved. The traffic optimization also connected to that. And also the smart task allocation, because also the task contains inside the, it is within this shell. And yeah, as I said earlier, the scalability integration is much easier. And with that, as you can see on the right side, we can put a digital twin on top with the help of 5G and also the AIS. And with that, the real-time synchronization, which has already started, which has already started with AIS, can be even more improved with digital twin in real time, which can lead to, for example, predictive maintenance, which can analyze the AMR's performance to anticipate failures of the AMR, but also from other assets. We just took the AMR as a leading example, since it is the main asset in our trial. With that, a dynamic decision-making, I mean, we explained the decision-making before, the jobs before, that we can say to the AMR, okay, go from A to B. It can be more dynamic and more autonomous. And yeah, so this dynamic decision-making also leads to an adaptive response. And we think that with both of these technologies, the basic trial that we showcased today can be a really good enhancement to much more effectiveness within the production. And that would be it. Thank you for your attention and for listening. If there's any questions, feel free to ask.
I think there are a couple of questions by Lee. So I will take the first question. How long did the manual map creation take? I think it was around 15 to 20 minutes. And is the autonomous map creation possible? So it is possible, but since I mean, comparing it to like a Roomba, which creates its own map, the DFA is not a very predictable environment. So we have to see certain clearances of where the Husky can go or cannot go manually. Otherwise, it might cause safety problems. And that is why we did not do autonomous map creation. Also, the second question is, who determines if an object is dynamic or static? So, with the direction vector node that is running on the Husky itself, the multi-scan, if it does not sense that the object is static or is moving or not, if it is moving, it creates a direction vector for it, predicting where it is going. Otherwise, if it is not moving with respect to the Husky itself, then it determines it as static. Yeah, that's if there are any other questions, let me know.
No other questions yet?
No.
Okay. We can maybe wait a minute. People proceed a lot of information. Wait. I see Roland is formulating a question.
Hey, Roland, how are you?
There is one more question from Chris.
Oh, okay. Nice to see you here.
Yeah.
Is there any question? Okay. Do you know what difference in average speed you can achieve? Oh, thanks a lot. Do you know what difference in average speed you can achieve with 5G connection? So that sort of testing. Okay. So yeah, with the 5G connection, I think our main goal was to check the range within the DFA, and we get 5G connection all over the DFA premises, and um, average speed distance speed for the network. I think it was barely any because we all, I mean, it was not, it was comparable with Wi-Fi as well because um, in a controlled scenario where like we have a test bed here, so the we want top of the line Wi-Fi connectivity with all our devices and 5G connection. I would say the main difference was with the range. So not all devices would get the same amount of Wi-Fi strength throughout the DFA, but the 5G connection with the cradle point or with the hardware that the DIMA had, it was pretty much consistent throughout the factory floor.
Yeah, I would like to add to that that we also have a demonstrator and a DFA that shows the comparison of the Wi-Fi to 5G, and there is basically a graphic that shows the latency between those two.
That's the difference. Yeah.
connections. Yeah, so the key idea is that over 5G we have almost like close to the straight line, and over 5G you have a lot of jumps in latency. So that's why 5G is more stable, as I would say, in that sense.
Any other questions? Is there? No?
Not yet.
Was somebody typing?
One more comment. Just asking you to gauge how much increased productivity can be achieved. Express in this per shift. In my opinion, this is not an important question. It convince the industry to use 5G. I mean, I think for to answer this question, we would have to do uh, like a longer testing so that we can have uh, that sort of those numbers in terms of how it can improve the workflow And I think, I mean, for us, after realizing it, after realizing this trial, at least like a few months of testing with the whole trial integrated with our workflow is able to give such a number. But I think with the routing set, it's kind of more reliable using 5G with a 5G antenna than Wi-Fi. But thanks for the nice question.
No comment. Yeah.
Thanks.
Already typing?
No.
Okay. Let's wait 3 minutes.
Yeah.
So we wait a few seconds for another possible questions. You're welcome. Also, thanks for the collaboration. It wouldn't be possible without our partner SIG. Okay, if there aren't, always again, thank you. If there aren't any other questions, I will thank you again for your attention, also for your curiosity and the questions. And yeah. Of course.
Of course. If you have any more, just let us know.
Yeah, you can mail us also afterwards,
Yeah.
and yeah, we are in close contact anyways. Then I will say to all of you, have a nice day. And thank you again for your attention and for having interest in our topic and our trial. And yeah, I will say have a nice day and goodbye from the three of us.
Thank you.
Thank you.
Bye.
Goodbye. Ciao, ciao.
You stay in? Or?
Yes.
Oh, Olivier, yeah.
I think we can leave.
Yeah. Okay.
Yeah.